at local max and min points. Wherever the gradient is equal to 0, we'll have a stationary point. And this can be a max, a min, or a point of inflection, and we've spoken about that in 12.4. In this problem, we need to identify the max and min points for this function h of x. And it's in partially factorised form. So we've got x minus 2 squared multiplied by x minus 4 squared plus 1. If we just look at the x's, then it's going to be clear to us we're going to have an x squared multiplied by an x squared, and that will be obviously a quartic. If I consider the coefficients, I've got positive 1 and positive 1, and if we square that, it's going to be positive as well. So overall, the coefficient of the x to the power of 4 is going to be positive. So what we're going to see here is that we're going to have 3 turning points, and it's going to be an upright parabolic shape. So how do we go about it? We take the h of x function, we expand out x minus 2 squared and x minus 4 squared. We then apply FOIL to expand out these brackets, and you can see it's very long, and we collect like terms. Clearly you can see now in expanded form that h of x is a quartic. What I do next is work out the derivative. And I can take out 4 as a common factor, and that will leave me with this cubic. What I want to do here is factorise this derivative and then set that derivative to equal 0 and apply the null factor law to identify the x values for where there are turning points. So we've got this cubic, and I'm going to call that p of x. Try different values of x to sub into it and see which one produces a 0. And you can see here, if I sub in 2 into p of x, I get a 0. And that will tell me that x minus 2 is a factor. So now applying long division, I put in my cubic. I divide by the found linear factor. And you can see my process through here. And I end up with that quadratic. So that now enables me to say this cubic here can be factorised to become x minus 2 being multiplied by this particular quadratic. Now this quadratic can be factorised using PSF or the grid method or whatever method you like to become x minus 3 multiplied by x minus 4. So now I have the derivative in factorised format. I'm looking to apply the null factor law. So I have h prime of x equaling 0. And that's equal to the right-hand side here. Of course, if I divide both sides by 4 and then apply the null factor law, I see the x values are 2, 3, and 4. Now, I need to work out the corresponding y values. So, of course, I don't sub in those values into the derivative. I sub them into the original function h of x. And if I do so, you can see that h of 2 is equal to 1, so there's a turning point at 2, 1. h of 3 is equal to 2, turning point at 3, 2, and we can see that our last turning point is at 4, 1. Notice that with our h of x function, that it's only being given a domain between 1 and 5. Whoops. And it's including the 1 and including the 5 with the square brackets. So we're interested in our endpoints. h of 1 is 10, so 1, 10, and h of 5 is also 10, so 5, 10. So with this, we have all the information that we need to do a sketch. I place in the turning points, and I place in the endpoints, and it's clear that there's only one way of drawing this graph, and that's shown in blue. The local minimums are at 2, 1 and 4, 1, and the local max is at 3, 2. Notice that it's a local maximum turning point. It's not the overall maximum of the function, it's just around this area here. The minimum value of h of x is 1, so the lowest value that we achieve for h of x is 1, yet the highest value that we have is 10 for h of x. And that's achieved for where x is equal to 1 or x is equal to 5. So that's how we do this kind of question by hand. At the bottom of this page, we cover the steps to do the previous question using CAS, and I'm just going to show you that. Our first job is to define the function h of x. So I'm going to go Menu, Actions, Define, and h of x is going to equal the bracket x minus 2 to the power of 2 being multiplied by the bracket x minus 4 to the power of 2 plus 1. But there's also a domain restriction, so I'm going to put that domain in. So given that, x is going to be between 1 and 5. And you'll notice that with the domain restriction from the original question, it had square brackets, and therefore that tells us that we're including the 1 and including the 5, hence these symbols. So there it is defined. So how is it that we identify the x values for the turning points of h of x? Well, we want the derivative to equal 0. So I'm going to go Menu, Algebra and Solve. I'm going to use the solve function, and now I'm going to use the derivative function, so Menu, Calculus, Derivative. I want h of x to equal 0, and I'm solving for x. Just a reminder, the way that the CAS calculator works is from the inside working out. So the first job the CAS is going to do is recall what h of x is. It is then going to work out the derivative of h of x. It's going to make that equal to 0 and then give us the x values that suit. You can see the x values here, and now to evaluate the y values, I sub those found x values into the original rule. So h of 2, h of 3, h of 4. So now I have the found actual turning points. I don't know what the turning points are. I could perform a sign diagram on that, but it's going to be very clear to us when we look at the graph. Also the endpoints. So remember we started at x equaling 1, so what's h of 1? This will come out as 10, and then the other right-hand endpoint was 5, so h of 5 will also come out as 10. So we have all the information that we found by hand, obviously much quicker in our CAS. Let's look at a graph for this. So to the home screen, and we're looking at the graph, and we're doing h of x. And you can see it's shown for us. It's the same shape as what we did by hand. I can change my window settings here easily. So Menu, Window Settings, and I might just go from -1 to 6, and I might go from -1 to 12, and that will give us plenty to look at. All right, so there's my graph. Of course, you can't really identify whether or not the endpoints are included or excluded, but whenever you draw this, you need to be very careful. If we were excluding the endpoints, then these would be hollow circles. If we're including them, then they are completed circles, filled in circles.